Hello everyone, so I think I'm clearly audible. So anybody can. Okay, okay, fine. So the plan for today is uh, I'll first show some examples, right? Starting from the definition of DFA and FA, like how we can start with an NFA, then ultimately get the corresponding DFA. And after doing that, Atul will discuss with the practice questions. Okay. So that is the plan for today. So let me share my screen. So this white screen is visible, right, to all? You can talk, otherwise I cannot see the chat or this thing because I'm on a different window.
Yes, sir, this is visible.
Okay. Okay. So, in the first lecture, you might have seen that there is a detailed discussion like and why this theory of computation is required. So the main point is given a problem, so definitely it's a decision problem, so whose result could be yes or no or true or false. So given this kind of decision problem, the first thing, can we compute it at all given a constraint resource? So constraint resource, whenever I say, I'm mainly saying the memory, right? So we assume certain type of constraint machines, right? A machine with very much constraint, which is I'm having a finite number of memory and we have to read the input in one scan, right? Then we'll go for a machine which is having a stack based memory, right? So like this, we are having type of machines where we are having different capability of the memory, and accordingly we want to find out, given this constraint, what kind of problem could be solved, right? And how efficiently we can solve them. So in the week one, we talk about a kind of a machine which is the kind of most constrained machine. If I talked about most constrained of machine, means they are having the lowest kind of resource. So they can solve the problem which are kind of a easiest problem. Right. Now these problems in terms of theory of computations, we say they are presented as a string and set of string as a language, right? And the particular string is accepted or not accepted, that decides the division problem results in a yes or no. Then we talked about we have two things for the given string or language or set of string or language. Um, we talked about that if you have to check the acceptance, right, a string is accepted or not, then we need a machine, right, which is a constraint machine. So the kind of languages we have discussed in week one, for them we are having finite automata or FSM, right? Finite state machines. Finite state means I'm having finite memories, right? And little bit we have given, but we'll go in detail in week two that we can also have a grammar, which basically is a generator for this kind of strings or languages. Right? So let us talk about the machine, right? Try to understand how these machines can be created, what are the differences, and what are the equivalence between the machines. Right? So we talked about two kind of machines, basically one kind of machine only, but I say the classification could be in two. So we call them as a DFA and something called as a NFA. So in both the cases, we basically define the machine with five tuples. So suppose the name of the machine is given as a M. So how do I define it? I give five tuples as a Q. Then we call this as a sigma. That's basically the called as a alphabet. Then we will have a function called as a delta, a set of functions called as delta. Then Q0 and F. So please note, usually whenever I like write something in a small case, I means it's a single element, but whenever I write something on a caps, it usually means it is a set. Now what a DFA, a deterministic machine, supposed to have? So first is Q. So Q implies to a finite set of states. Then we have this sigma, which calls as an alphabet. It's basically a finite set of symbols. Then we have delta. Delta is a function. So in terms of function, we can write it given a state and given a input, given a state and given a input, it will map me to another state. In a simple way, Q, suppose I am having certain states in my automata, DFA, Q1, Q2, Q2, these are my states, right? Now, um, my inputs are 0 and 1. And if we say that delta Q0 and 0, so if I am currently on state Q0 and my input is a 0, suppose I go to the state Q1. Right? This is called as a transition function. This calls as a transition function. Now every DFA having a single start state, and if you can have multiple final state, it is a set of final. Professors sometimes use some term as an accepting set. It's basically a set. So this is what we have. Um, so how do I draw it? Let us, in a simple way, I just give a, I draw it is as a randomly. Suppose I have something called as a Q0. I say it's a starting state. Now I say given a 0, I'm on Q0. Given a input 0, I go to Q1. Now given a 1, whenever I'm on Q1, I go to Q2, right? So this is something I have. So what are my transition functions? So my transitions functions will be, sorry, delta Q0 given 0, I go to Q1, delta Q1, then given 1, I go to Q2. So this is called the initial state, which is marked as an incoming arrow, and a final state kept into a double cycle, right? Circle. Whenever I call it as a deterministic, for each state, for each input, there will be only one transition. For each state, for each input, there will be exactly one transition. Now the question is, for Q0, where is the transition for 1? So for 0, there is a transition, but for 1 also there has to be a transition. Now one thing you can do, you can assume about a state which I called as a date state, which I called as a date state. So where I keep all the transitions which are not actually required for my main purpose, right? For building my language. So here I have one, I can have a zero. Right? Similarly, for Q2 also, suppose you have to have the 0 and 1, both the transitions are missing. So you can, so what will happen if you have certain inputs which are not desired, right? So you send them to a date state. Now the point is like you may not mention a date state in a DFA, then it's called as a partial DFA. And if you want to have the full-fledged DFA, you need to give the date state and you have to show all the transitions. So, but remember, this is something unreachable in the way because this is no way direct you to the accepting. So, string anyway diverted to the date state that never come back to a final state. So, your string is dead means it is not going to be accepted. The question is now, what is the NFA? So, NFA is much more generalized way to represent a machine. So DFA having a constraint given a state, right? For each input, there is exactly one transition. But NFA do not have that constraint. NFA say given a state, given an input, you can have more than one transition, or you may not have a transition also. Right? So what I mean to say, what I mean to say, uh, show you what is possible in NFA. So suppose there is a transition for 0, a for a delta, if you have a q0 and input is a 0, you get q0. At the same time, for 0, you can have q1. Now, what I'm saying, given q0 and given a 0, you can either go to q0 or you can also go to q1. So this is called as a non-determinism, right? You're not sure either will go to q0 and or q1, so you have to check for both the paths, like which is suitable for your string. Another thing might happen whenever it's a non-deterministic, without input also you might move from one state to another state. So without giving a 0 or 1, you can move to from one state to another state, so it's called a empty string. It's called a epsilon transition, so which will be like q1 given epsilon, there is no input, you go to q2. Right. So these are important points. Again, I repeat the difference in DFA. For each state, for each given input, there is exactly one transition, right? But in NFA, they do not have this condition. So for each state, for each input, you can have more transition. And secondly, you can have epsilon transitions also. So without having an input, you can move from one state to another state. Okay. So now, what are the differences we get in the presentation? So suppose NFA, so let me name it as an M1 and I name it as a M2. So I'll have Q. Uh, so symbols are all going to be same, right? Now, what are the differences? Like how do I present it rather, I'll say. So first is Q is the same, is a finite set of states. It's going to be the same. Sigma is also going to be the set. It's a finite set of input symbols. Symbols. Now delta is interesting. What delta will do? So For delta, there will be a little difference. Given a queue, a state, right? Given a input. Now this input can also, so if I say 0 and 1, you need to understand it is not only 0 and 1 for NFA, it is also include this epsilon, right? Because you need to understand without input also you can transit, right? So delta can work with 0 and 1 as an input, also with without any input. So how do I represent without any input? I say it's a empty string, that's a epsilon. So if I just write a sigma with epsilon, that means your inputs along with epsilon input. But what you transit to, you can transit to 2 to the power q, which is basically uh, is called a power set. Power set of q. So what is that? So given your q is q0 and q1, right? What is your power set? The power set can have empty, so all the subsets of q, right? Then you can have q0. So it's called the empty set, right? Q0, q1, and q0 and q1. So you need to understand, since it is a non-deterministic, right? Given an input, you might go to more than one state also, right? And it can be any subset of the queue. It can be any subset of the queue. So that's why if I have two state in a DFA or NFA, you can have a transition. Suppose for one, suppose you can have a transition for delta, given your input is q0 and input symbol is 1, you can either go to q0 or also go to q1 because it's non-deterministic, right? So this is one key point. q0, the starting symbol will be remain as a starting symbol, but we'll write it as a set because each set over here is a set. And finally we'll have the f, right, which is the set of set of final states. So this is what we have as a DFA and NFA. Now we'll just check out how intuitively we can create a DFA or NFA, right? So suppose I want to represent a string. So I want to represent rather a language. Language is a set of strings. So uh, what I specifically want to do, I want to represent all the strings. I want to represent all the strings which ends with a AB. Which ends with a AB. So how do I do it? So ends with a AB means it could have only AB. It could have AB. It can have AB. It can have BB. Like this. Anything ends with a AB. So how do I write this set formally? I say L. The language is a set of the strings. So these are all strings. I say L is a string which consists of each string, right, which contains or which basically ends with AB. Right. Now I have to create a machine, a finite automata, which will accept all the strings which ends with a AB, or in other way, which will accept the language L. So I'll say I want to design a machine which will accept L. We write it like this: machine to accept the language L. So I find NFA is always easier to draw because It's more flexible, right? You can do any kind of transition, even you can do a transition without an input. So there are a lot of flexibility. So let us do it with two parts. The first part we think about only the situation where the ends it's AB. Right? That means I should have a transition with the A, right, which will get me to Q1, and I should have a B, which will get me to the final state Q2. So I'll have something like this, right? So at the end, what I'll have A and B. So that is done. Now, before AB, what I can have? Before AB, I can have any combination of A and B. Before AB, I can have any combination of AB, and it could repeat n number of times, 0 to n number of times, right? 0 to n number of times. So how do I do it? The next part I write it in another color so that it becomes easy to understand. I take another state Q0 and I take 0 or 1. So what I'm saying over here, if you have 0 or, sorry, not A, 0 or 1, I'm taking A and B, right? Sorry, A and B. Or if you have confusion to understand this, this is basically same as writing it given A, given B. It's same thing. You can also write it together A slash B. It's the same thing. So that a self loop say uh, you can have number of A's, right? It is on a loop or number of B repeatedly, but end has to be AB. End has to be always AB, right? Okay. So let us go for having a DFA for the same, but DFA having a problem that, not a problem, having a constraint that we cannot have more than one transition for a given state and input. See, here is a problem. Why it is a NFA? You have to see this is Q0, right? Given a, you come to Q0, then from A, Q0, you can go to Q1 also. It's better to present it as a transition table, right? So how do I draw a transition table for this NFA? I'll have a state, then I'll have input A, I'll have input B. Remember, whenever you're drawing an NFA, it's better to have an epsilon also because you can have transition for epsilon also. In this case, it's not required, but I can have a situation, right? So what are your states? You are having, for NFA, we normally write them as a set. You're having a Q0, right? Now, given A, where you go, you can go to either Q0 or Q1. So I'll write it as a set Q0, comma, Q1. Given B, you come back to Q0. You go to a empty state. Now, for Q1, what I have, for Q1, given A, the empty state. For given B, for given B, I go to Q2. For null, it is again empty. For Q2, all null. Right. So this is how to present it as a this thing. So be little bit cautious if you want to show input state. We basically give a incoming arrow, and to present which is my final state, you give a star. Right. So which clarifies okay, this is my starting state and this is my ending state. Now go for a DFA. Let us go for a DFA. Again, the ends we know that I have to end with a and B. So there should be A. If I get a A, then next I should get a B so that I can reach the end. So that I can reach the end. Now I add the next part. I should have a starting symbol from where it will start. So I give Q0 also. Now the question is, I cannot do like NFA because I cannot have two transitions for A from Q0, right? That is not possible. But what I can have, I can always have a transition for B because for B there is no transition is given for Q0. So that is quite possible. So I can have a number of B, I can have number of B before AB. But how do I say I can have also number of A before AB? This only say I can have number of B before AB, but how do I say I can also have number of A before AB? So suppose, let me also draw this transition table so you can make it much more easier way without having much confusion. So starting state is Q0, so you don't have to write it as a set because they are not subsets, right? So Q0, right? So Q0, given a A, you go to a Q1, given a B, you go for Q0. So now for Q0, you cannot write any more transitions, right? Because for given a state, for one input, you can have only one transition. So done for Q0, nothing can do with the Q0. Now what I can do with Q1? Now for Q1, right, given a B, I go to the final state Q2. But given a A, what will happen? Right? Given a A, what will happen? Now, if it is a A, then I cannot reach to the final state. So what I can do, I can return it back to the start state. So that if it is a A, I'll say go back, have as many as A's. But whenever finally you ends up with the A's, then goes for a B, then reach the final. Right. So that means for Q1, if you have a A, then you have a Q0 over here. Now go to the Q2. Right. You go to a Q2. Now what if, right? You have few A, then after that you want to have few B. Then again ends with a AB. Suppose I want to have AA, BB, then ends with a AB. For the timing what I have, I can have AAA dot dot dot, then ends with a AB. I can also have BB, whatever it is, I ends with a AB. I also solved the problem that I can have, this is also solved, right? I can have A, A, B, B, A, B. Okay, this is also solved. So for Q2, what I can do, I cannot end up with two B's, right? I cannot end up with two B's. What I can do in safe way, if I get a B, to just return it back to Q0, because if I get a AB, and that is not the end, again I'm getting a B, then again starts from Q0, right? So this is safely what I can draw. Even I think for A also you can return it back because I can again ends with the AB. Right. So you can check it out once this one is cut. We'll do a conversion from NFA and DFA. We'll verify this part we are getting or not. So that will be fine. Okay, so this is one example I have shown you, okay, how we can have NFA and DFA and how we can write the transition tables. So just want to check out. Up to this, is it okay? Hello.
Yes, sir.
So are we back to the screen? You can see my screen, right?
Yes, sir, this is visible.
Okay. Okay. So what I need to do, I need to relate a machine between two machines. If I have a DFA machine and another machine, so are they equivalent, or which is powerful in that way, right? So how do I say two machines are equivalent? Suppose I am having two machines, M1 and M2. I want to check whether they are equivalent or not. Right? So I'll say they are equivalent if and only if uh, the language accepted by M1 is same as language accepted by M2. In another way, uh, in another way, you can say M1 accepts W, which means M2 will also accept. So they will accept the same set of strings, right? If you have two machines and they are accepting two set of strings, then their equivalence. And what we want to show that a DFA machine and a NFA machine, they're equivalent. Right? So for each NFA, you can also have an equivalent DFA. And remember, all the DFAs are by default a NFA only. It's a trivial, right? Because um, as I told, like a NFA is a generalized form of a DFA. So all the DFAs are by default NFA because NFA say there is no limits on the transitions. Right? You can have 0 to n number of transitions given a state or given an input symbol. But just a constant put on the DFA that you can have a single transition. That's all. So all the DFA can be treated as a NFA. That's why all the DFAs are trivially can be converted into a NFA. But all the NFA also can be converted into a equivalent DFA. Remember, NFA is more flexible in the sense for us for drawing it, right? To build the system. But otherwise, they are same powerful, right? So they are having powerful in the sense accepting the languages. So what are the languages can be accepted by a TFA can be accepted by also NFA. The reverse is also true. Anything accepted by NFA can be also accepted by TFA. So since DFA to NFA is a trivial thing, so by default all the DFAs are NFAs. So we'll just do the reverse one. Like given a NFA, how I can go to a DFA because DFA machines are much more having certain restrictions, right? So algorithmically, we have two versions of it. One is if my NFA don't have a epsilon transition, what I'll do, and second version say uh, if my NFA having a epsilon transition, what should be my approach? But remember, the second version implicitly covered the first version also. So let us do it separately so that it becomes easy to understand. So first, uh, I have a machine M, which is a NFA. I'll have a Q summation, not summation, sigma delta, then Q0 F. This is my mm, NFA machine. I want to create the equivalent TFA machine. That's M dash. I'll get new states. I'll get new states, right? And why I'll get new states, I'll discuss because it's if you have a queue, a finite set, right? So in DFA, It becomes a subset of the power set of the queue, right? Then your alphabets remain the same because the input symbol won't be changed, but delta will be changed because your transitions will be much more restricted, right? You cannot have multiple transitions for the given same input and states. And your final state, sorry, Q0, this will be changed, and there will be a dash. Uh, One correction, just to think, what
Sir, even the starting state changes if we convert an NFA to a DFA.
given
If we convert an NFA to a DFA, does the starting state change as well?
starting state actually do not send change in that way, but I'll show you. Okay, just one correction. I have mistaken something. I'll just make it. It is not a set. It's a Q0 only. Okay, I'll show you. I just confused between this thing. I'm not on it. Okay. Okay. Yes, it will be changed in a mathematical way, but logically you can see it remains the same. I'll show you. Okay. So how do you relate, right? Uh, so NFA is given. So I need to present corresponding DFA symbols, right? So what will become the Q dash? What will be Q dash now? The Q dash become a subset of the power set of 2 to the power Q, which is basically the power set of Q. Then second, there is no change in the input symbols. There is no change in the input symbols, right? Now, what is delta 1? What is delta 1? Now, how do I write? Now, say for each state S, right? Uh, now, let me write it as a capital because it's a set. For all capital S belongs to Q dash. What does it means? Q dash is a power set, right? Q dash is a power set. That means if my Q is Q0, Q1, Q2, my Q dash is null set Q0, Q1, Q2, Q0, Q1, Q0, Q2, Q1, Q2, Q0, Q0, Q1, Q2. 1, 2, 3, 4, 5, 6, 7, 8. So it's a 2 to the power 3, right? 8. Correct. So, uh, so these are my supposed to be the state in the DFA, right? Which are the subset of the states of the queue. So um, let us assume कि what are qualified. So this is qualified supposed to be a set to be an state in Q1. So I'll rather say Q1 is a subset of this. Right? Suppose this is eligible, and this is eligible. So let me write Q dash. So these are reachable, I'll say. So it's basically a subset of the power set. So suppose I say this is Q1, Q2, Q0, Q1, Q0, Q1, Q2. Now think about a situation. So these each set becomes a state in DFA. Up to this clear, right? Up to this, is it clear?
Yes, sir.
Each subset becomes a state inside Q1. So whenever I'm defining a delta, a transition function, suppose my alpha is A and B, right? Suppose I try to define the transition for the state Q0, Q1, right? With given A. So how do I define this delta dash? It will be delta Q0 given A with union with delta Q1 with A, right? Similarly, if I want to compute the new transitions for the state Q0, Q1, Q2 given B, so what it will be? It will be delta. So this I'll get from the NFA. Q0 for B what I have, union with delta Q1, B what I have, then union Q2 for B what I have. So what the state I'll get, that is the transition for this entire state for given B. Right. Now, this is what I say here. Now, I say for each state S, which is a set, right? Each state in Q1 is a set. Is the term is clear what I'm saying? Each state in Q1 is a set, right? It could be this, or this, right? So, for each state, I need to now define the, for each state, I need to define the delta. So, how do I define the delta dash given S and given input symbol, suppose A. So A is belongs to sigma. So how do I define it? Just see here how do I define it. Right. It will be a union. It will be a union for every state Q which belongs to capital S. Then do what? Define delta. Why I'm writing ampersand for delta every time? Okay. Delta Q to A. Do you get it?
Yes, sir.
So if my state is this one, then I have to take the transition for Q0 and Q1, then I make a union of it. So what I get, that is the complete transition for this state given A. So that's how I redefine delta to delta 1. I redefine delta to delta 1.
So, sir,
Now,
in the new DFA that we have created, because the initial state can be a set itself, that's how it's different.
can you repeat your question?
Like here, Q naught dash
Yeah.
can be a set. Because of that, it's
Yeah.
different from Q naught.
Yeah. Yes. That's right. I
So
told mathematically it's a different. Yeah. Because
yeah,
as
so
I
it's a
told, each is
superset
a
of
set.
Q naught.
Yeah, each is a set. Now Q0 becomes just the Q0, but Q0 is a set. That's all.
Yeah.
That is what I say. So logically it's same, but mathematically presentation has to be this. Now this ape dash is very important. This ape dash has to be if, right? Given an intersection, let me write it as a set because it's a set, right? So writing set expression will be much easier to understand. So I say for each state S belongs to Q dash, belongs to Q dash. So for each set you are having belongs to the QS, sorry, Q dash, it will be included in F dash if S, right? If S intersecting with F is not equal to null. Means there is a common element between the final set and S. In a simple way, we'll say at least one final state from F will be in the final state in NFA. So in NFA, what are the final state? At least one has to be there in your this thing. So suppose, given an example, suppose in my DFA, sorry, NFA, this Q0 is the final state, right? Q2. Q2 is the final state. So which is eligible for become a final state over here? So your final state can be, so in a mathematical way, I take a intersection between this state and this state. So null. This state and this state Q2. So this is eligible, right? This state and final state null, nothing. So this state and this state Q2. So this is also. So this must be there. That's all. So any state having the final state of in DFA, that becomes a final state in your DFA. Is it okay up to this?
So one clarification here.
Yes.
Here we are saying that f dash is equals to a set of states if f intersection f is not equal to phi.
Yeah.
And we are using intersection here uh, because in DFA each state is a set itself, not an element. Were it an element,
No,
we could
no,
have
no.
just said,
That may not be. Yeah, that's okay. But what I meant to say, suppose your DF, sorry, NFA having two final state, so which is Q1, Q2, right?
yeah,
So in DFA, your final state then F is equal to Q1 and Q2. So which are eligible now to become my final state in this. If I take an intersection, this becomes also a final state. This and this become a final state. This and this again not. So all becomes final state now.
yeah.
So either this has to be there or this has to be there or both has to be there. That's all.
Yes, sir, but my question was that here we are saying S intersection S because the states in Q dash are sets,
Hmm.
but in states in Q are elements themselves, right?
Yes, yes.
So that's one difference.
But capital
And
F is a set of the final states. That is what I
yeah,
know. Yes.
okay. And
But
if this,
individual elements of F are a state.
okay, okay. And yeah, so my question here is that in NFA versus compared to DFA, the uh, set of states would be set of sets in one case and set of elements in another case. Uh,
Set of
like here in the DFA case,
set of
the set.
yes, yes, you are correct. Yeah. So
Okay,
each state in DFA becomes a set of the state of NFA.
okay, okay. Yeah, thank you.
Okay, so let us take an example then to finish with this without epsilon thing, right? Then we'll go for without epsilon. So whatever example we have done, let us do it for that only. That we have already drawn a NFA, right? So which I have a Q0 that ends with A and B, right? A, B, A, B, two. This is B. So for this one, I need to draw the corresponding DFA. Okay, let me go for it. So what I need to do, I'll first go for taking out the transition table. So let me take the transition table for NFA. So although I have taken it, let me take it again because in the same page it will be easier. So I'll have states. I have input symbol A. I'll have input symbol B. I'll have also epsilon. But I'm not taking it for the timing because we are not considering epsilon transition for the timing, right? So I have Q0. Given Q0A, I go to Q0 and Q1, right? Given B, I go to Q0. Okay. Please check it, okay? If I make some mistake by copying, that is a Q. If Q1 given A, I don't have anything, right? No transition. It's a null state. And given B, I go to the final state Q2. This is you may not write if it is without null. Q2, correct, right? This is for the NFA. Now for doing the DFA, what I can do in a straightforward manner, I can say Q0 will be Q0. This is for sure. So I'll start with a DFA. Mm, I'll have state, I'll have A, I'll have B, nothing else. I start with Q0. Now the point is like whenever I have an unexplored state, right, for which I haven't tested what will happen if I give A and B, I need to go on checking for my next input. Right? So given Q0, what I need to check, I need to find out what will be the delta dash, right, for given the state Q0. So what is given for A? So I can write it as a delta of Q0, Q0 with the A. So which is Q0, Q1. So I'll just write Q0, Q1. Now what will be the delta dash with Q0 given B? I'll have a delta Q0B. I'll have Q0. So Q0. After doing that, you need to check here and here. Do I have any unexplored state? Q0 I have already checked. But for A, I got Q0, Q1, which is unexplored. So this becomes a new state which I need to explore again, right? So I have to find out what are the delta dash transition for Q0, Q1. I say delta dash Q0, Q1. I give it for A. How do I do? I do delta with a Q0 with a A union delta Q union Q1 with a A. So Q0 with a A, I can go to Q0 Q1 with a A. It's a null. So I go to state Q0 Q1. So this given A, I go to Q0 Q1. I have to check what I go with B Q0 Q1 with a B with the delta Q0 with B union delta Q1 with a B. For Q0 with a B, I go to Q0 and Q1 with a B, I go to Q3. So that means I'm getting a new state Q0 and Q3. Now write it Q0 and Q3, which is the unexplored state. Because for this I have already done. But for this I have to still do it.
Sir, I think it's Q2, sir, not Q3.
Mm-hmm.
I think it should be Q naught, Q1, Q2. There's no Q3 state, I think.
This one is saying Q0 with B,
Okay, no, sir. Yeah.
Q1 with B, Q0 with B,
Q naught, Q3. Yeah.
Q naught, Q1 with B, Q2, sorry, Q2, Q3 I don't have only, right?
Yeah.
Sorry, sorry. Yeah, Q2. Yeah. So delta dash Q0, Q2 with a A, we'll have delta Q0, A, union with delta Q2, A, Q0 with A, Q0, Q1, union Q2 with Q2 with A, null, right? So Q0, Q1. Correct only, right? Q0, Q1. Okay. And just check it once. Okay, Q0 with a A, correct. Q2 with a A, correct. Then we'll have delta dash Q0, Q2 with B. So delta Q0 with B, union with delta Q2 with B. Q0 with B, Q0, Q2 with B, null. So that means it's a Q0. Now see, I don't have any unexplored, right? All are explored. Okay, so what will be my initial state? This. What will be my final state? So here the final state is Q2. So here any state having Q2 will become my final state. Only so this state having the Q2, so this becomes my final state. Now let us draw the DFA. So let me put the state first. So whenever you are drawing it, right? So technically correct thing is in the brackets also. So this is the initial state. Then Q0, Q1, another state. That will be another state. Q0, Q2. Its final state. Right? So just put the transition. So Q1 given a A, you go to Q0, Q1. Given a B, you back to Q0. Now Q0, Q1 given a A, you back to this. Given a B, you go here. Now, if you are on a final state, given a A, you go here. Right? And given a B, go here. We had a confusion there, no? This correct one, right? Got it right?
Yes, sir.
Sir, in the previous drawn NFA,
Mm-hmm.
the center node, center state, it is having self loop with A, no? A. That was not
Yes.
if you scroll up, you can see some here, NFA. In Q1,
Where I have done that? Yeah, this one. Yeah, this is I have drawn wrong. So that's why I was not able to find B that time. So Yeah, I've drawn wrong this one. So I was getting confused that time, right? I told we'll check it once we do the conversion. Like this. So no, this is A. This is A.
Sir, I don't think Q1 needs to have a self loop for Q1 dash to get a self loop.
Which one?
Like as Sujay was saying that in the original NFA, Q1 doesn't have a self loop for A, but that's not required for getting a self loop for Q1 dash, right?
You're asking for this one, right?
Yes.
No, no, you
Like
cannot do it like this. Like if this is having a self loop, I'll have a self loop. The point
yeah.
is like you need to get the same strings, right? But restricting the transitions, right? So the point is here, see, here I can have this self loop for B, but I cannot have the self loop for A over here, right? Because I have already written a transition for A. So that's why what we are doing, we are moving the self loop over here because for this already we are having B, so we can still have a, right?
Yes,
Because
sir.
A also can be repeated at the beginning, B also can be repeated, right? You can have the strings like A, then finishing with AB. You can also have B, 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 finishing with AB, right? So that is what is satisfying, right? But if you want to move to a DFA, since it is already having a transitions for A, you cannot give this self loop over here. So what? How do you satisfy this part? So you need to put here like then hello.
Yes, sir.
Getting my point right?
Yes, sir. I'm getting that.
Okay, then I'll go for now the with the transitions. With if silent transitions. It's basically the same, only you have some special rules for transition. So before I go into this, there is something called as a epsilon closer, which is written like this. So a set of states, given a set of states, sorry, let me show it for one state only first. Suppose I have a state called as a Q, right? Suppose I have a state for as a Q. So what is epsilon closer of Q? So it is set of all the states P such that such that from Q you can derive it through epsilon to P. What is that? You have a Q, you have a Q. Suppose you have IS, you have a T, you have a R. Okay. So you have here A, this is epsilon, this is epsilon. I'm not bothered about this. So if I ask what is epsilon closer of Q, so that is what is reachable from you with the epsilon transition. So that will be Q itself. So Q to Q, you do not need any symbol to do the transition, right? Then Q to S, without input you can go because it's a epsilon transition. T also you can go without any input, but for R you need an input. If I say what is epsilon closer of Q, it is Q along with all the state you can, you are having the epsilon transition. Now, given it is a set of state, because whenever I'll go for a DFA, I'll have a set of states, right? How do I find the epsilon closure of S? The same way, I'll say union, right? Union for each Q in S. For each Q in S, I'll get epsilon closure of Q. Do you get it? What I'm saying? Do you get it? What I'm saying?
Yes, sir.
Okay. Okay. Anyhow, if you are not very clear about it right now, during the example, it will be very clear. It's simple only. Okay. Okay. Let us define the things because what was our Q dash? Q dash was a subset of 2 to the power Q or the power set of Q, which will remain the same. Then I need to define what is delta for every state belongs to Q dash, right? For all the symbols belongs to sigma alphabet. Delta dash is of A. Previously, how we used to define it? Union S belongs to capital S. Delta of S comma A. So this is what I have done, right? Previously, whenever I have shown this, where I have done that, where I have shown the delta for the transition. This is equivalence, right? Where I have shown the delta. Yeah, here. Right. So this is what I have. It's exactly same, but only difference is since you are including the epsilon, it will be epsilon closure of this. Or what you can do, you can take epsilon closure of this. So this is simplification of the thing. I'll show you if you do this simplification mathematically, it becomes easier to solve the problem. That's all. So it is epsilon closure of union of all the transition for the elements of the set S. Okay. What will be your Q0 dash? It will be a set Q0. The F dash definition will remain the same. So I'm not again writing it. Right. Oh, sorry. One thing is F dash will remain same, but there will be slight difference in Q dash. It will be again uh, epsilon closure of Q0. You suppose you have a start state, right? Q0. Right. From Q0 with the epsilon transition, you can go to Q1. That means in your DFA, since you cannot have epsilon transition, this Q0, Q1 both will become your start state. Right?
Sir, one question regarding this.
Yes.
If we have multiple start states, then how can the implementation look like? Because
In
if we are going to
DFA,
start,
for DFA you cannot have multiple start state, right? But for
okay,
NFA, suppose you have Q1, Q2, Q3, all of your are your start state. What do we do in NFA? So that we can do a transition, I make Q0 as a start state and make a epsilon transition. It's same, right? Q1, Q2, Q3 is the start state. Have you got it?
yes, sir. And just one more thing here in the above
Just,
example you
just
showed.
let me repeat it once again if it is not
Okay,
clear
okay.
for anybody else. Suppose in my NFA, I'm having multiple start states, right? So Q1, Q2, Q3, all are my start state. Q4. I don't bother what you have next. So you have something. Now what I'm saying here, I have to have one start state. So what I can do, I can take additional start state over here, and I can make if silent transitions, right? So that's all my problem. Yes, what is the next question?
In the above example that you made, one with QRST,
Ah.
here there's an epsilon transition from Q to every other state, and suppose S2 has epsilon transitions going forward.
Yes, yes,
To,
that also will be included. So if
yeah,
there is a PQRSTU, so this is also epsilon. This is to be safe, write it as a star. Why I want to
okay,
say Q to Q, it is without any epsilon because star means 0 to n number of repetition. Q to S, 1 epsilon. Q to U, 2 epsilon, right? If you write a Q asterisk, right, then it includes 0 to n number of epsilon transition. So this is much correct. Yeah, good point you have told. I have to be much more mathematical correct in this way. Understood, right?
yes, sir.
Okay, so let me go for one example. Which example I will take? Let me check. Which I can do quickly. All epsilon, if you give me everything, become very big. So that's the problem. So, okay, so I'm doing what Sarah has done. Okay, so that's also easier understanding. So that is better. All strings over 0 and 1 that either starts with 1 or ends with 0 1. So what I have, all the strings which will start with a 1 and ends with a 0 1. So how do I do it? If I want to draw a NFA, if I just consider the constraint, so one is we need to end with 0 and 1. That means I can have a Q1, then 0, Q2, and 1 Q3. Before that, I can have anything, I don't bother. So before that, I can have 0 slash 1. So it is basically, if I write this like this, it is basically writing A and B separately. I can write it together like this. It's both 0 and 1. So this is any string over 0 and 1 ending with 0 and 1. And if you want another string that start with 1, then beginning will be 1, but at the end I can have 0 and 1 anything. Right? Now, so this is what, now eventually this is could be your start state, this is also your start state. But as I want to say it is part of the same automata, what I can have, I can have a common start state Q0, and I can simply have a epsilon transition. So basically I have two machines initially. I have created a machine which will having all the string ending with 0 1, I have another automata, all the strings starting with the 1. Then I have merged them with a single state, right? It becomes a single automata which do both. Sorry, either or. Is it clear up to this?
Yes, sir.
Okay. So let us write the NFA transition table states. Okay, A, B, epsilon. Don't forget to write the epsilon, okay? So Q0 is my start state. So Q0, right? Then Q1 with A, sorry, A not A, this was 0 and 1, right? Q1 with 0, we go to Q1 or Q2, right? Q1 with 1, Q1. There's no null transition, right? Sorry, epsilon transition, Q2. In few books, instead of epsilon, they use a lambda transition. Okay, it's basically the same thing. Q2 or Q2 for 0, there is no transition. Q2 given 1, so Q3, no epsilon. Then Q3, no transition is given. Okay, then Q4, Q5. Okay. So what will be my Q dash? Q0 dash. Tell me, it should be epsilon closure of starting state Q0. So what will be it? It will be Q0 with epsilon. What I can do? I can go to Q1, Q4. So eventually this becomes my starting state for my corresponding DFA. So if I write the state 0 and 1, my starting state will be Q0, Q1, Q2. It will be very big. Okay, anyway. Mm, so delta dash Q0, Q1, Q2, 0. That will be epsilon closure of Q0, 0, delta Q1, 0, and delta Q2, 0. Then delta Q0, 0, this. Then delta Q1, 0, Q1, Q2, union. Q2, 0, epsilon closure of Q1, Q2. Now we have to check the epsilon for Q1 and Q2. So Q1 and Q2 both are null. So epsilon closure of these two will be Q1, Q2, which is again a new state. U2. I have to do it for one also. Mm, delta dash Q0, Q1, Q2 with 1, right? It will be epsilon closer of delta Q0, 1 union with delta Q1, 1 union with delta Q2, 1, which is epsilon closer of Q0 1. Q0 with 1 is Q1. Q1 with 1. Q1 with 1. Sorry.
Sir, Q0.
Q0 with 1 is Q0 with 1 is empty, right? Hmm. Q1 with 1, Q1. Q2 with 1, Q3. It's epsilon closer of Q1, Q3. I need to check the lambda transition for Q1 and Q3. Q and Q3 both are null. So this is Q1, Q3. This will become Q1, Q3. So then again you need to bring Q1, Q2, explode this for 0 and 1. So I'm not completing it. I think it's okay, right? You can do it. So until and unless there is no new state is getting created, you have to go on repeating it. Is it okay? Can you finish it? If you cannot do, I'll help you afterwards.
Yes, sir. One question regarding this is that I actually made a different NFA compared to yours because yours had epsilon transitions while mine doesn't.
Hmm.
So multiple NFAs for a single language are possible.
Yes, but DFA is not possible.
Okay, so DSA is always unique.
DFA is deterministic, right? You'll have exact.
Yeah.
But NFA can be different because you can introduce epsilon anywhere, right?
Okay.
Every time you introduce a epsilon, you'll have an extra state, right?
Yeah.
So, yeah, Atul, you want to go for practice questions a bit, or any doubt you people having week 1?
I actually have one from the practice assignment for week 1.
Okay, so anyhow, Atul will do that. Yeah, Atul, then you can go for it.
Okay, okay. Okay, sir. Thanks. So let me share my screen. One second. Yeah, I hope my screen is visible. So as sir have covered most of the things and recap all the things of the week 1. So I think the week 1 practice assignment we will discuss. So and most of them I think is covered. So you can go through that and you can answer that. So let's one by one discuss these practice assignment questions. So first question is regarding the DFA. Okay, so a deterministic finite automata is defined by strictly structural constraint that distinguish it from other model of computation. Select all statement that correctly describe the structural property of DFA. So here you can answer that. So which statement is correctly describe the correct structure property of DFA? So first option, a DFA may allow more than one outgoing transition for the same input symbol from the given state. Is this correct?
No.
because this is not valid for the DFA, because in DFA every transaction is well defined, so you can move only the one state by reading the only one input symbol. So that is well defined, so you cannot move to the multiple state with the one input symbol. So the first statement is not correct. Here second, a DFA has exactly one designated start state. Is this true?
Yes.
Yeah. So first statement is not correct. Second statement is true. As we have covered this. So a DFA may include null transition that do not consume input symbol. So this is not correct for DFA. This is true for NFA. Okay. So null transaction, this epsilon transaction is not allowed for DFA. So this is also not correct. So let's fourth option, for every state and every input symbol in the alphabet, the next state is uniquely determined. Is this true for the DFA?
Yes.
Yes, correct. So as I already mentioned for the option one, so this is the well defined in the DFA. So as deterministic, so every step is well defined. So this is correct for the DFA. A DFA may consist of infinitely many state. Is this true?
It shouldn't be because we call them finite
Finite
automators.
state. As we have written the definition of DFA, we have mentioned that states are finite. So this is not true for the DFA. Okay. So for the first question, this option 2 and option 4 is the correct property. So let's move to the next. Okay, second. A non-deterministic finite automata NFA process an input string and generate multiple computation path. Okay, during the computation, some path terminate without consuming the entire input string, while at least one path consume the complete input and ends in an accepting state. What is the correct outcome for the input string? So as mentioned that suppose if we have q0 is the initial state, we can move multiple state for the one input symbol in the NFA. So like suppose we are moving from q0 to with zero input symbol, we are moving suppose q1, and second is like q2, same input symbol we are moving like q3, we are moving with the next state with same input symbol. So multiple is possibility is there. So means when we check our string is accepted or not, so we will move to the each possible state. So suppose if any string is started from 0, so we will check from each q0 to q1. So like this will become like a tree structure. So we are starting from q0, and one path we are moving to q1. Okay, and second path we are moving from q0 to q2 with the same. Okay, and third path we are moving from q0 to q3, and lower it should be anything because it depends on the string. So what input strings we are checking. So if some of the path will terminate without accepting, and maybe some of the path will terminate with accepting the complete input string. So according to the NFA, what is the outcome for this process? So NFA, so which option is correct according to you? The input string is rejected because not all computation path consume the entire input. So this is the first option. Is this correct?
That's false.
That's a false. Yeah. The input string is accepted because at least one computation path consume the entire input and ends in an accepting state. Is this true?
Yes, because
Yeah.
at least one path. Yeah.
So at least one path terminate with accepting state, okay, and I consume the entire input string. So we consider that string is accepted. Okay, doesn't matter what about the another paths is if they are terminating with the accepting state or not, if they are terminating with the they are consuming the complete input string or not. At least one path should terminate and consuming the entire string with accepting state. So that's the definition of NFA. So we will consider that string is accepted by the NFA. So this is the option correct, and this is MCQ. So other option definitely will be incorrect. So the input string is rejected because some computation path terminate early. So this is not correct according to the NFA. The outcome is undefined because NFA may produce multiple computational paths. So this is also not correct for the NFA. So option 2 is correct for this. Okay. So let's move to the next third. Yeah. So consider the DFA below. So this is the DFA diagram. Automata is given here. So start symbol is predefined, as well as this is also a final state, because start and this double circle is denoting to the final state. So you can just uh, observe this and figure out that what type of string this is accepting. Okay. So if you see this, this is start state is itself a final state. So means this this epsilon means empty strings. So this will also accept a empty string. So this is the first thing, because without any movement, without any input symbol reading, we are at the final state. So means empty string is also considered as a accepting state, as accepting string. Other than this, you can see we can move from this path. So you can go from A to Q2, and you can come back to this. So this is the one possibility. You can accept the strings like that contain 0 1 0 1. So this is just like a loop. So 0 1, this type of string is actually will accept. And another possibility is the another loop you can see in this way. Okay, so you are going from A to Q1, and here you can also loop with the same state Q1. Okay, so that will again generate the 1 as an input symbol, and then Q2, and then come back to A. So in this way, you will get like 1 0 1. This is the point that you are reaching to the final state, and you can also get like 1 1 by the one transition A to Q1 1, and after that you can repeat multiple time this Q1. So and that will generate like multiple 1, and after that you will get 0 and 1. Okay, so 0 and 1. So last will be also 1, and there is no outgoing transaction from this side Q1 to Q0. So there is no movement possible here. And if you are coming from this side, like uh, A to this Q2, okay, so that is 0. And from here you can again go to like Q2 to Q0. So that will also produce 0, and here also multiple zeros are there, so that multiple 0 is also there. So after that this 1 1, and then multiple 1 are possible, and then that same cycle will be done which we have already covered. So like this 1 0 1. Okay, so what is the outcome if you will see, if you will see each option? So what type of string are accepting by this DFA? So all binary string that ends with 1 0 1. Okay, this is correct, because okay, so along with this empty string and 0 1. So if you see overall, we are getting this type of string. So all the strings which are ending with 1 0 1, because after getting like 0 1, if you repeat again in this, so then you will get like 0 1 one more time. So this is ending with 1 0 1. So this is also completing with 1 0 1. Other than if you are coming from any another path, so still you will get like this. So if from here 1, and then 0, and then 1. So all possibility are there. So you will end with 1 0 1. And this is the one case where we are considering the empty string is also accepted. So this statement is correct. This is also correct, and this one is also correct. Okay, so option 1 is true. All binary string that end with 0 1. So this is not the only string that will end with 0 1. Okay, so here empty string is also there. So this statement is not covering the whole, because 1 0 1 is, we can say this is also ending with this, and 0 1 is also ending with this, but this empty string is not covered with this. So this is not correct. All binary string that contain odd number of ones and even number of 0. So this is also not true, because we are accepting 1 0 1. So here this odd number of ones are there. Sorry, not there. You can see even number of ones there. So that is a counterexample. So this will be not true. All binary string that start and end with 1. Okay, so this is also not true because we can accept just 0 1. Okay, so this is not starting with 1. Okay, we have already seen. So only the option 1 is satisfying, which what strings this DFA is accepting. Okay, if you have any question, you can interrupt in between and you can ask. Okay, so let this epsilon closure, this Q, denote the set of state reachable from a state Q using 0 or more null transition in an NFA. Which one of the following is not a property of null closure? So, which options here we are asking which one of the following is not a property of null closure? So, reflexivity, is this a property of null closure? This epsilon closure?
Yes, sir, because any state would be reachable to
Yeah,
itself.
from the itself, yes. Okay, so that is true. Transitivity is also true because if you have suppose q0 and you are moving from like your q1 with epsilon and q1 to then this with this epsilon you are moving to q2, so we can say that we are also moving from q0 to q2 with epsilon, okay, without consuming any input. So this is also true. So first and second are true. Depends on input symbol.
So I don't understand the third and fourth options, like what they mean regarding
No,
epsilon
no. Are
closure.
we using any input symbol for this null closure? We are considering this in null closure. Sorry, this epsilon closure.
No.
No, we are not considering any input symbol. No? What are the input symbols we are given for the DFA? We are not including that for calculating this null closure. We are only
Okay.
including this epsilon things where we can move without consuming any input. So that we are
Okay.
calculating only.
So only
So
the transition matters, not
yes,
the
yes,
input
not the
symbols.
input symbols. Yes. So this is not depends on the input symbol. Okay, independence from the input alphabet. So yeah, this is correct. Okay. So answer for this question is option third because we are asking the not a property of null clause.
Okay,
So
so here third and fourth option basically talk about the same thing, just one is
yes,
saying independence, other is independence.
yes, yes. Both are
Okay,
the just
okay.
reverse. Okay. Huh. Non-deterministic finite automata NFA may include this epsilon transition which permit state change without consuming input symbols. Select all the statements that correctly describe the behavior and purpose of null transition in NFAs. Okay, so where we can use this epsilon transition in the NFA and what are the purpose possible. Okay, so epsilon transition allow an NFA to move between state without reading any input symbol. So this is the main purpose. I think this is correct.
Yes.
Okay, so we can move from any one state to another state without consuming any input. So this is the main purpose. And epsilon transition consume exactly one input symbol before changing state. So this is not correct because we are not using any input symbol for this. Epsilon transition may be taken even after the entire input string has been processed. Is this true?
Yes.
Yeah, is this true? Suppose final state, multiple final states are there. Okay, like this QF1, QF2, QF3. Okay, so still we can connect with, we can make one final state like this, and we just mention epsilon like this. Okay, so that will work as the same as the if this is the final state. Okay, so we are not reading any input symbol, so we can add like this to make one final state for each. Okay, so this is correct. The presence of this is correct. The presence of epsilon transition prevents an NFA from being converted into a equivalent DFA. Is this true?
That's false.
False. We have already done just before. Okay, so this is false. And epsilon transition provide a convenient mechanism for simplifying the construction of NFA. So this is true because we can easily create a NFA with the help of like this epsilon transition. Suppose if we have multiple type of multiple demand for the language, so we can make a different separate DFA for separate demand, and we can combine using with this epsilon with the start state like this. So that provide the like easy mechanism to construct the NFA. So this is again true, but both have the same power. So NFA and DFA both have the same power. Okay, so this first, third, and fifth option is correct for this question number 5. Okay. So next is this. So consider the following partial transition table for of a deterministic finite automata DFA with state set Q, and this input alphabets are given, start state is mentioned, and set of accepting states are given. So you can make a automata diagram with the help of this state transition table. So like q0 is given as a start state. Okay, and after that you have q1, q2, q3. Okay, so q1, let's, so q0 to q1 with 0. Okay, and q0 to q2, suppose this is a q2 and this is with 1, and q1 to q0, so q1 to q0 like this. So this is with 0, and q1 to q3, this is the new one, q3, and this is with 1, and q2 to q3, so this is with 0, q2 to q3, q2 to q3, okay, 0, and q2 to this is not given, so I'm just writing like this, so that this is question mark with 1. Okay, and q3 to 0 with this q2, this, and q3 to 1 like q1, this one. Okay, so this automata is given, just I have draw the diagram for this given transition table and this definition. So q0 and q2 are the final state. Okay, so this is again q2 are the final state for this. Okay, now just check what should be the transition from q2 to 1. So that means what should be the state for this next state for this input symbol. So this accept exactly all binary string containing an even number of zeros. Okay, so even number of zeros, which state should be the transition of delta q2 to 1 we define. Okay, so 4 states are given, so all states are given here, so you can just validate that how this automata is working. So you can see even number of that zeros how we are getting. So q0 is itself a uh, final state. Okay, so means this empty string is also generating by this. Okay, because we are currently a start state and without consuming any input, so we are also reaching at the final state. So empty string is also there. So empty string means number of even zero is actually 0. Okay, no. So now other possibilities, you can move from q0 to q1, and you if you come back to q0, so means 2 0 will be consumed. Okay, if you use this cycle, so you will always get a even number of zeros. Okay, 2 to 4 like this. Okay, and 2 4 6 any even number or empty string is now done. Now other than this means you can use any number of ones before this, in between this, and after this like this. So any possibility is there. So how this is actually getting the all possibility. So you can put this even number of 0 at the starting with the this iteration, and after that you can use this ones count. So q1 to q3, now you can move to 1. If you want to use more number of ones, so you can come back to q1 like this, and again like this one. And after that, you can suppose you are coming from 1 0, say q0 to q1, and so like this string 0 1 0. Okay, here also the number of zeros are even. Okay, so you can come through this like, so q0 to q1, and then q3, and from here this q2. Okay, so again these are the number of even possibility. And again, if you can, here you can also loop through this, so you can come back to q2 to q3 again, and like q0. Okay, so that will produce 2 every time, 2 0. So that will be remain the even number of zeros. So what is the possibility for here? So what we can do, so after the 0 we can put any number of ones again. Okay, so then it will become a cycle. So like you can use any number of zeros at the initial, then you can use number of ones after that, then you can again you multi applied the number of zeros. Same things you can again enter to the number of ones from this q1. So if you put this q2 to q0 with 1, so this is will be, this will generate like a, if you want to end with number of ones. Okay, but before that you will satisfy the number of zeros that will remain even. So you can put this uh, q2 to q0. So that is the one answer for this. If you try like others in q2 to q1, you will see you will get a like a counter example, so that number of 0 will not remain even. Okay.
Sir, in this one I actually got wrong, and I entered Q2 as the answer, and I'm not really sure why
So that
it's
is
the
the
wrong
one,
answer.
that is not a wrong answer actually. So I have also checked this. So if you use this also instead of this one, okay, still you will accept all this in number of
Yeah.
events. Okay, so both are, I think, correct. So we will still verify this. So I have also checked this. So if you put this one with the self, okay, so that still you can accept all type of strings with this condition, or you can reject all other strings. Okay, so both are the possible answer here.
Okay. Got it.
Okay, so this is not correct. Definitely. If you will try to this transition, you will definitely find some strings without for fulfilling this definition. Okay, so we will check this, or after that, maybe we will make this MSQ. Okay. Okay, so this is straightforward. So match the following. So language. So this L means language. So what type of type set of strings that can be accept? So here this is empty. So if there is no string inside this set, so means this is a empty language. Okay. This is like a empty language with empty string. So this is definition like this. So this is the matching from first to B. Okay, so this is empty language, and this is a language with empty string. Okay, so one string is possible. So like if you can make this q0 and like this. Okay, so here this is a language, this will accept the language, so that will make a empty strings. Okay, L equal to AB. So this is the definition. So this is straightforward. Last, so language consisting of any combination of A comma B. So that is the last option. Hmm. Okay, so consider the given statement S1 for every NFA. There is an equivalent DFA. So as we have discussed in the initial part of this session, so NFA is the equivalent to the DFA. Okay, so as power for what is the power of NFA? So same power is for the DFA. If we can simply convert NFA to DFA or DFA to NFA, so both are equivalent actually. So this statement is correct. As to finite state machine can recognize palindrome. Is this true?
So we need a push down automata, something like that.
Yes, we required a memory to maintain the previous what we have already recognized, okay, what we have already covered in the past. So we require some memory to find out the palindrome. So we cannot finite state machine cannot be recognize palindrome, because here all things are actually fixed. Memory is also limited. Okay, so this is just like a unbounded things. So palindrome is a maybe a unbounded things. So we required a memory for that. So that is not possible to accept by the finite state machine. So some examples are discussed. So like what is accepted by the finite automata. So that some regular language can only be accepted. So non-regular language cannot be accepted by the finite statement automata. So this palindrome is the example. This is not a regular. Okay. So that will also cover in the big two content, what is regular, non-regular, all the things, language, all the things will be covered in the big two content. So this will not be accepted by the finite state machine. If finite state machine cannot recognize language that require an unbounded amount of memory. So this is the reason for this one. Okay. So this is true, as three option is true. Because finite state machine cannot recognize language that require a unbounded memory. So like if you want to check the parenthesis matching balance, okay, so parenthesis balance, so you required some like which was the previous opening parenthesis and correspond what are the closing parenthesis. So some memory is required, and that is unbounded, so that finite statement cannot recognize. Okay, so only the first and third option is true. So means option third is correct. Okay, so now see this NFA. This is the NFA. Okay, so I think we have taken this example in this initial part. The language generated by the above NFA consists of, what is the answer? String that end with 0. Is this always true? What is the minimum string that it will accept actually? So this is q0 to q1, okay, and means 0, and then q1 to q2. So this is the minimum part. So this finite automata, this NFA will actually accept. This is the smallest part. Before this, okay, so before this, this loop, this may generate any number of 0 and any number of 1. So initial may be anything, okay, and may also be any number of zeros. Okay, so like you can just count as take, and here one, or this is the combination of 0 and 1. Okay, so like 0 plus 1 like this, and you can make the as take. So this is the type of this language it will actually accept. So here string that end with 0, so that is not true, because we can also accept 0 and 1 with this. Okay, so this is the minimum, so this is not ending with 0. String that start with 0 and end with 0, that is also not true. It maybe start with 1 by this, okay, self loop. So that is also not true. String that contains 010 as a substring, so that is also not true. We have already seen this minimum length strings, which is accepted by this. So that not contain this as a subset, so this is not true. String that contain 01 as substring and end with 0 or uh, 01. Okay, so here both are included actually. So either it contains the 01, okay, and end with 0. So if any 0 is included like this, or end with 01, so that is by default. Okay, so suppose if this loop q2 loop is running, so that definitely string will terminate with 0. So this is considered here, or either 01 by this. Okay, so the last option is covering all the language which is accepted by this NFA. Okay, so this is the explanation for ninth. Okay, so this is again come from the properties we have discussed today in the initial session. So given an NFA with exactly 10 state in total, which includes the initial state, 4 final state, and a dead state, find the maximum number of state in the equivalent DFA obtained using the subset construction. what is the maximum possibility for subset construction here?
So like 2 to the power 10, so
So 2 to the
1024.
power n. So that's simply 2 to the power 10. You can calculate here, and that is 1024. So this is a straightforward answer for this. Okay. So during the conversion of non-deterministic finite automata NFA to an equivalent deterministic finite automata using the subset construction method, the construction process proceed by generating DFA state corresponding to subset of NFA state. When does the subset construction process terminate? So this is again the we have already done this process. So when we actually stop the process, once we actually not found any new subset state. Okay, we don't not found any new subset construction, so that we stop the process. So that is the straightforward answer. When no new subset of NFA state are generated by further transition. So this is the correct option for this. So this is the reason we will stop the process. Uh, so this is straightforward. Okay. Okay. So let M, this is the machine. So Q, that alphabets sigma, delta, Q0, FV, the non-deterministic finite automata, NFE, where Q is the finite set of. So this is the definition given here for this machine, NFE. Let M dash this be the deterministic finite automata DFA obtained from M. Okay, so some this NFA is given. We have obtained the the deterministic finite automata for the given machine using subset construction. Each DFA state is a subset S. Okay, and that is the subset of Q. Okay, suppose that after reading a string W that belongs to alpha star, the DFA is in state SW, that is a subset of Q. Which of the following best describe what SW represent here? So here S is just like a set of, as we have already covered this. Here when we are creating the DFA, so this is just like a subset construction. So from the NFA, so we are just combining the states and we are making a subset like from that states. Okay, so this is also a one that DFA state is each DFA state is a subset S that belong to Q. Suppose that after reading a string W that belongs to that sigma star, that DFA is in state SW. So after reading that W string, okay, so DFA is in state this. Which of the following best describe that SW represent? So what is this SW represent in this option? So the set of NFA state reachable from Q0 by reading exactly the symbol of W, ignoring all null moves. So here, this statement here till now, this statement is okay, but ignoring all null moves is not correct. Okay. So where actually we are moving, so W may be any substrings like this, and we are just starting from the starting state, and we are moving, we are just reading the input symbol and we are reaching at some state. So what are the set of NFA states reachable from Q0 by reading exactly the symbol of W? Okay, so here we are talking about the NFA. Okay, so the condition are given from the DFA, so that SW is representing the set of NFA state that reachable from Q0 by reading the exactly this. But ignoring all null moves, that is not correct, because we can include that null moves that also in this. Okay, so null is just like a without consume any input symbol, so that will also be included. So this statement is incorrect because of this. The set of NFA state that appears in at least one accepting computation path on input W. So this is also not given here. So that this reading the string W, the set of all NFA state that appears in at least one accepting. No, no. Suppose that after reading a string W, that will DFA start a state SW that will Q, which is So that is not given that this string is added. So one second, the set of all NFA state that appears in at least one accepting computation path. This is also not true because the set of all NFA state that appears in at least one accepting computation path. So that is also not true because it may be reject also. Okay. This is not given here, so this is accepted or not. So this may be reject condition also. And set of all NFA state reachable from Q0 by reading W and allowing null moves at any point. So if any null transition is also there, so that will also be covered. So this actually covered the condition. So what are the set of states from Q0 after reading all the string W, including this null moves at any time from any state? So that will also include that. So that is correct. A set of all NFA state reachable from any state in Q by reading W. So this is again not covering the complete definition. Okay, so this is also not correct. So option C is the correct answer for this. Okay, so this is again on the same line. So here M is the, let M be a null, this epsilon and NFA for a state Q that belongs to capital Q set. Sorry, let its null closure of epsilon this EQ denote the set of all state reachable from Q using 0 or more this epsilon transition. Suppose a new epsilon transition is added from some step P that is belongs to Q to another state R belongs to Q without changing any other transition of the NFA. Let the resulting this epsilon NFA be denoted by M dash. Okay, so what is given here? We have some this epsilon NFA, null NFA. So we have just modified little bit. Okay, so we have just added one more this transition, this epsilon transition in that, and we have again the same another NFA. Okay, that is M1. Okay, we have one M and another is M1. Now we are comparing this. So the let D and D1 be the DFA obtained from M and M1 respectively using the subset construction method. So D is constructed from M and D1 is constructed from that updated M1. Which of the following statement must hold? Okay. So the start state of D1 may be different from the start state of D. Is this true? Here it is mentioned may. Okay, so this is not guaranteed, but it may be true. Is this true or not? Start state.
Yes, it can be different because
Hmm.
if we have multiple starting states, then by adding epsilon to all of
Yes.
them, we can create
Suppose
another
we
state.
have like this null epsilon to q1. Okay, and we have some q2 difference some with input symbol. But if suppose if we added like one transition with epsilon, so this q2 will also be added as a starting state. So it may be different. The number of so this statement is true. The number of reachable state in D1 must be greater than that in D. Number of reachable state. So are the number of reachable state will changed?
Here, the number of reachable states refers to the number of states
Yeah, when
in the
we
automata
construct
itself.
when we construct the NFA to DFA, so we start from Q0. So what is the next state we created? Okay, so that where we are actually reaching from Q0. So that is just like a subset construction method. What new subset are generating, new state are generating for the DFA. So that number of states will be here. It is mentioned the number of reachable state must. This is not the guaranteed actually. Okay, so it remain the same as well. Okay, this because of this must, it is not correct. This is not always true. like. Okay, so the number of reachable state in D1 will always be like greater than the D because of this additional one transition.
So here, because we are adding an epsilon transition from P to R, R is now in the epsilon closure of P,
Hmm.
right? But if it were already in the epsilon closure of P before even adding this epsilon
Yes.
transition, in
Hmm.
that case, D and D1 would both be equivalent.
Equivalent remains same. Number of D1 and D both remains same. Because of that,
Yeah,
it is not correct. Here it is mentioned it must be greater than.
yeah, got
Okay,
it.
so that is the reason. The set of accepting state in D1 may be different from the set of accepting state in D. This is correct. Okay, here again the may is given, so that may be affected if final state we have added and we again added some epsilon things. So the accepting state may be changed because of this epsilon closure. Okay, so option 3 may be possible. The language accepted by D1 must be different from language accepted by D. This is not true. So adding epsilon transition will not change the language. Both will accept the same language. Okay, so this option is that oh must be different. So this is not correct. Okay, language will be remain same. So option first and third is correct. Finite automata are well suited for recognizing patterns describing by regular language. So as I mentioned in the previous example, so that accept the regular language but are limited in their expressive power. Which of the following problems can be modeled using finite automata? So these are some examples given and covered in the lectures also. So what are the problems which cannot be accepted by the finite automata? What comes in the different category? Okay, not regular type of language. So checking whether a string is valid identifier according to the fixed lexical rules. So you have given some lexical rules like a password. If you are checking your password, follow the specific or like in the programming language you have the identifier no? So that you check always start it should contain only the alphabets or numeric things, so that rules actually are given, so that can be validated with the help of this finite automata. So this can be okay, so this is possible because of with the help of this finite automata. This verify whether parentheses in a strings are balanced. So this is not possible by the finite state machine. Here we require a unbounded memory for that. So that will not be covered. That not comes under the regular language. Okay, so this will not be accepted. Validate an email address. This is similar to your validate identifier with the same set some set of rule. Here it is again validating an email address under a simply fight set of syntactic rule. Okay, so this can also be accepted by the finite automata, detecting an occurrence of fixed substring within a string. So this is also a fixed substring is given, so that we can uh, validate from the finite automata. So only this second is cannot be accepted by the finite automata. Okay, this comes under the non-regular. So this is the answer. And fourth, yeah, this is directly from the lecture. So as we have already covered today. So let delta star denote the extended transition function of non-deterministic finite automata NFA with start state Q0 and set of accepting state F for an input string W belongs to that this sigma star, and delta star is the extension. Okay, extended transition function Q0 to W denotes the set of state reachable after processing W, under which condition is the string W accepted by the NFA. Okay, here an accepted is given. So we have multiple paths. Okay, from for this movement transition. So at least one of the path should be reached to the final state. So means if we will check this transition, so like so this one second. So this delta star Q0 comma W that belongs to final state. So that is not possible actually for each path. Okay, so we cannot say that this will always belongs to this this transition will always belongs to a final state. So what is the state we are reaching by after this, that will always belongs to a final state in NFA. So that is not the always true, because we have multiple paths, so other paths may be terminate without reaching to the final state. So again, this is equal to final state. This is also not correct. Here this is the things that covers the concept. So that okay, delta star q0w, and then where we are reaching, what state we are reaching, and we are getting this intersection with final state. If that is not equal to this empty, means some common final states are there. Okay, so all paths here, this is representing all computing paths. So if any of the transition we are getting the intersection between final states, and that is not actually empty. So we can say that our string is accepted, string w is accepted. Okay, so this is covered in the lecture itself, and taken from directly from the lecture, so you can go through that point. And again, this is, so all the p that belongs to that transition, this transaction, and p belongs to final state. So this is again the same, what are the states that belongs to this this transition, and p is belongs to final state. So that is also not always true. Okay, so here this third option is the correct definition to correct condition to identify the string is accepted by the NFA or not with this extended transition function.
Sir, for
Hmm.
last option, instead of for all p, if we say there exists p, then it is also correct, no?
Yeah, there is, yeah, then we can say that yeah, this is correct, because some of the state in the each path, like, then that belongs to f. Hmm.
Okay,
Correct.
thank you.
Sir, can you explain that last option?
So that this p is like a states that belongs to the states, like where we are reaching for all the paths. Okay, so is asterisk is representing the all paths that we are coming from the starting state. Okay, so that that p belongs to the all, actually here it is given all state where we are actually reaching at the last state, that all belongs to final state.
Okay,
Okay, so this is not the true, all may not be actually belongs to final state. At least
okay,
any one of the like final path may be reached to the final state, then we can accept that that is the that string is accepted.
but because here it's saying for all, then this option shouldn't be true. If it was
Yeah,
saying if there exists some p, then that will be true.
that will be true.
Okay.
Okay. Yeah, so these are the practice assignment question. You can go through the graded assignments. You can try to solve that. And I think professor have also leave some practice question in each lecture at the end. You can also try to solve with the on the paper and pen, because this is just like a some hands-on type of course. So you have to draw the finite automata for the example by your own. Then you will understand better. Yeah. Okay, so that's the practice assignment we have covered. Uh, Anything else from your side?
Yes, so just one question regarding the course itself, that would it be covering some concepts from compiler design, or is it just strictly TOC?
No, we have the compiler design, the next listed course.
Oh, so it will be coming up.
Yes, after this course, maybe next term or maybe next to next term, the compiler design will separate course. Will
Okay,
be we will
okay.
come up and with the same professor. Okay, so this mostly cover the this or finite automata, this DFA things. But yeah, compiler design, the initial part is this just like a TOC. After that, this all the phases, all the that layers are there. Then we will cover separately in the different course. Okay,
So are there any plans for introducing computer organization as well?
Computer organization. We have one CST course in this. We are actually planning, but Arup sir, are you there?
Yes, yes.
So, any plan for computer organization course
Not right
separately?
now.
Not no. Yeah.
Okay.
But yeah, we are planning to just covered all the like gate CS courses. Okay, so computer network is there, OS is there, TOC is there, compiler will come, and other data structure this is there already.
So
Right.
only discrete maths and computer organization architecture is
Discrete
not
math
there.
is also I think
It
included,
is
or maybe
coming May only.
all
Wait, discrete math will come in the May.
may.
If you want this organization architecture, please write mail to Bharti ma'am and all. So
Yeah.
maybe you can plan it accordingly.
Sir, although the team is introducing subjects relevant for the GATE CS exam as well, but because of the course structure itself, not a lot of people would be able to take them up because there's some requirements that you have to do certain BP subjects, certain BD subjects, certain humanities subjects, and all that.
That I cannot
So,
help you. So you need to
yeah,
write all these things as your feedback.
okay,
But that definitely you can do this one. Organization architecture, because this is only one course which will be not there. Right? So otherwise, all the things are clear now covered in very detail. So I can
yeah.
stop the recording, I feel, right?
Yes, sir. Yes.